Hello, welcome to a recording of Chapter 15 lecture where we are learning about traveling waves and sound. This is going to set us up for the kind of last 2/3 of the course where we talk about electromagnetic waves. But before we get to those, we're going to introduce waves from a kind of more physical standpoint, one that you might be more familiar with. So we're going to talk first about the different ways we model waves, okay? A wave model describes the basic property of waves, and it emphasizes those aspects of wave behavior that's common to all waves, like electromagnetic waves, or, waves in the water, okay? Or even sound waves, right? The math that we're going to do to describe waves is going to apply to all different types of waves. These waves are moving, they're traveling, and what a traveling wave is, it's an organized disturbance, okay? We're going to talk about what is being disturbed and what that means in terms of waves. And the other thing about traveling waves is they move with a well-defined speed. So the kind of wave that you might know about already, or when you first think of the word waves, is waves in the water. Waves or ripples on the surface of water are mechanical waves, and that's because these waves are generated by the collective motion of all of the water molecules, okay? And the motion of the water molecules is what is being disturbed, right? The water molecules on a still pond are just sitting still until you throw a rock in there, and those water molecules are starting to oscillate up and down, right? They're bobbing up and down, creating these ripples in the surface of the water. So what's being disturbed is the water's position, the position of, maybe one water molecule, okay? So that's what's being disturbed, is the position of the water molecules. And the medium is the substance in which the disturbance is occurring. So in this case, the medium is water. So the disturbance is created by a source, like the rock being thrown into the pond. And the waves are moving at a certain speed outward, right? So these ripples are moving outward at a particular speed v, called the wave speed. It's important to note here that a wave transfers energy, but the medium does not travel, right? Energy is used to create the up and down motion of the water molecules, and that is certainly moving, but the water molecules themselves are not traveling with speed v. They're simply moving up and down. So, but remaining in the same position. So we're going to be going back to this idea a lot. What's moving in a wave and what's not moving in a wave. So let's, to kind of round out our introduction into waves, right? We have mechanical waves, like waves on a string or waves in water. And then you also have electromagnetic waves, okay? Electromagnetic waves are encompass things like light, radio waves, microwaves, okay? Waves coming from the 5G towers. And the thing about electromagnetic waves is they don't require a medium to travel through, right? You don't need air molecules. You don't need anything for the waves to travel through. Electromagnetic waves can travel in vacuum, which is the absence of any atoms or molecules. And then finally, matter waves are a type of wave-like characteristic that we assign to some particles. And we're going to learn more about matter waves at the very end of the course. I think, somewhere in chapters 27 through 29. Okay. Electromagnetic waves, this is going to make up chapters 20 through 28. Okay. So, but what to remember is all these wave phenomenon and wave math that we're going to learn can be applied to all different types of waves. So we can characterize mechanical waves in terms of a transverse or a longitudinal wave. And a transverse wave is when the disturbance is occurring in a direction that's transverse or 90 degrees, right, or perpendicular to the motion or the speed of the wave. I'm sorry, not the motion, the speed, right? So when we shake a rope, each little piece of rope here is moving up or down, right? And that up-down direction is 90 degrees to the wave's movement direction, which is to the right. So that's transverse wave. Longitudinal wave, a little bit harder to see, but a longitudinal wave is the motion, the collective motion of the particles that make up that object. So in this case, like the slinky wires, they're actually moving to the left and to the right, oscillating about an equilibrium position. And that left-right is along the same direction as the wave speed. So that's a longitudinal wave, right? Longitudinal means like parallel. So the motion of the object is parallel to the motion or the speed of the wave. Earthquakes. Earthquakes are a type of wave, right? It's a wave, a disturbance in Earth's crust. Earthquakes come in both longitudinal and transverse flavors, right? We call S waves transverse waves and P waves longitudinal waves. So let's take a look at a disturbance in Earth's crust done by a P wave of an earthquake. So the motion of the ground is like it's shaking. Like imagine you have like a little box of rocks and you shake the box left and right, right? The rocks are going to roll a little bit to the left. They're going to roll a little bit to the right. That's what's happening to Earth's crust. It's moving to the left and to the right. And the Earth's crust itself is not, moving all the way to the right. It's not moving from mile 1 to mile 25, right? It's shaking about an equilibrium position. So the motion of the ground is shaking to the left and to the right. The motion or speed of the wave is also moving to the right. So this is a longitudinal wave. Maybe when you think of earthquakes, you think of the earth shaking up and down, right? And it does do that too. So the Earth's crust is actually going to be moving up and down, vibrating kind of, right, as the crust slips down under one of the other plates. There's actually different reasons for earthquakes. That's only one cause of an earthquake, is when the one plate slips under another plate. And there's other reasons for earthquakes too, but just as a way to think about it, what's happening is that can cause, right, whatever the cause of the earthquake is, it caused the ground to shake up and down. So the motion of the ground is going to be 90 degrees or transverse to the motion of the wave. So these, motion of the wave, what's the motion? It's traveling. The wave is moving, okay? The wave is moving from one end of the thing to the other end of the thing. It's a traveling wave. So we're going to be able to describe these traveling waves. When you drop a pebble into the water, right, it creates ripples, and those ripples travel outward, right? So we're going to look at how mechanical waves travel through a medium. And just as we did in the previous few slides, we're going to make sure that we distinguish between the motion of the wave and the motion of the medium, right? So if the wave is moving to the right and the medium is moving up and down, let's just say in the y direction, then this is a transverse wave, right? If the wave is moving to the right and the medium is moving along the x direction, this is a longitudinal wave. So that's what we mean by distinguishing between the two. We can't exactly use Newton's laws on waves because, waves are a collective motion of many, many particles, right? But if you isolate one particle, let's say you take a piece of rope and you isolate one little particle in the rope, you could use Newton's laws, okay? But when we're looking at waves, we're looking at the entire wave. So typically we're not going to be using Newton's laws to solve any problems. But like I said, we can take a look at a piece of string, we can analyze Newton's laws, and we can kind of understand why when we shake a string, you see that bump traveling through the string. okay? So this is just to give us an idea of like why this wave is traveling. It does use Newton's laws to explain it, okay? But to classify and describe the entire wave, we're not gonna exactly use Newton's laws. So let's kind of get a microscope out, right? And let's get a string or a rope and let's shake it and cause that wave to happen. So we're gonna examine this little piece of string right here. And if we do that, we can apply Newton's laws to that little tiny segment of string. And what you see is that you have tension on the string kind of pointing up from where that lift in the string is. And then you have kind of some pointing down. And if you were to add up all the forces, the net force would point in an upward direction, right? That would be the net force. If you add those two t vectors together, you're going to get a result of a vector pointing up. And that is what's lifting that part of the rope. So we know that this wave is traveling to the right, right? So we look at that same piece after the wave has moved to the right. Well, now let's examine the direction of the tensions and add them up. The net force due to those two tensions when the wave is when that dot is at the peak of the wave is going to be pointing down. And so that means that the wave is going to start, or that piece of rope is going to start moving down after the wave has passed through it. Right? So we're just kind of microscopically examining one little piece of rope to help us understand what exactly is causing the rope to move. But now we're going to zoom back out and look at the collective, wave, all the pieces together. This is just explaining what I just explained on the previous slide. Okay, so let's do this quick check and then we'll move on to the next section. So a wave on a string is traveling to the right. At this instant, the motion of the piece of string marked with a dot is doing what? What is this section of rope marked by the dot about to do? So how can we figure that out? The wave is traveling to the right, so let's draw the wave at some other instant in time, right? So we do that by just drawing another wave right next to it, okay? That wave is moving to the right. So can you visualize that, right? The blue has shifted to the right and become the red. And so now we take that same piece of string that marked by the black dot, right? And now it's up here, okay? Right? Because remember each location of the string, each little piece of the string is not actually moving to the left or the right. It's only moving up and down, right? Because this is a transverse wave. So now we can see that that little part of the string has moved up. And that is the direction that the string is moving at that moment, up. Okay? So we talked about mechanical waves, waves on a string, waves in the water. We even mentioned electromagnetic waves. Sound waves are another type of wave. Sound waves are mechanical waves. Okay, so they are mechanical waves because you need a medium in order to hear sound, right? You need a medium. I'm a nerd, right? Obviously, I watch Star Trek, and there is like a famous line in an old Star Trek movie, or maybe it was also in this horror movie called Event Horizon, which is like a sci-fi horror movie. You should totally check it out if you're into horror movies. The quote is, "No one can hear you scream in space." Okay, that's because sound doesn't travel in vacuum. Okay, if there are no molecules in the air and you're in vacuum, sound will not travel. That's because sound waves are mechanical waves requiring a medium to travel in. So what is that? What is a sound wave? A sound wave is a pressure wave. It's a motion of the molecules in the medium, and the motion of those molecules are left and right. It's a longitudinal wave. So how does a speaker work? This might help you understand what a sound wave is. If you've ever ripped off the screen of a speaker and you look at a speaker, there's a little circular rubbery piece that's called the diaphragm of the speaker. And to produce sound, that diaphragm moves to the left and to the right. It kind of bumps out and sucks back in. And what it's doing is it's pushing the air molecules, It's pushing them, causing a region of compression where there's a high density of molecules. And then it creates like a little void over here, which is called a rarefaction, when it's like a low density region of molecules. And so this is a longitudinal wave because these molecules are being shifted left and right from their equilibrium position, and the sound wave is moving to the left or to the right. So it's a longitudinal wave caused by disturbances in the air, right? The molecules in the air being disturbed from the left and to the right. So, regardless of if we're dealing with a sound wave or a wave on a string or a wave in the water or a wave in Earth's crust, okay? A property of a traveling wave is that the wave speed does not depend on the size and shape of the thing we do to create the wave, the pulse. It doesn't matter how we shake the string, okay? Doesn't matter how the rock is thrown. It doesn't matter how the speaker, what frequency the speaker is at, okay? None of that matters. None of that affects the wave's speed. The only thing that affects the wave's speed is the medium itself. So, looking at strings, right? The properties, the string is the medium. So the properties of the medium are going to govern the speed of the wave. So for a wave on a string, the properties that govern the wave speed are the mass to length ratio, which is given by the letter mu. The linear density is another way to describe the mass to length ratio. So this is the linear density of the string. Okay, so it tells you how much or how little the waves are going to move. And so the other property is the tension. The tension in the string is going to govern how quickly the wave moves. And so if we combine these together, the velocity of the wave on a string is going to be equal to the square root of the tension in the string divided by the mass per unit length. Okay, so only material or medium properties affect the velocity of the string. So let's take a look at this example. We have spiders. Spiders are involved. Spiders live on webs. Webs are a bunch of strings, right? So we are going to be doing something about calculating the velocity of the web, right? Because we're given the mass per unit length and we're given the tension. So obviously we're going to need to calculate the velocity and for what purpose. So we're given all this information and we're asked at the end, finally, if an insect lands in the web 30 centimeters from the spider, how long will it take for the spider to find out? So we're going to need to be using the velocity, right? Which is the square root of tension over mass per unit length, right? And we were given the tension. We were given the mass per unit length. And so we can find the velocity. 200 meters per second. That's pretty fast, right? So that spider is, going to be sitting on a bunch of strings where the speed of the wave on those strings is 200 meters per second. And so what's going to happen is when that insect lands on the web, that's going to be our wave pulse, right? That's going to cause a disturbance in the web. And the wave is going to travel a speed of 200 meters per second towards the spider. So if the spider is 30 centimeters away, how long does it take for the spider to feel the wave? That's how we kind of rephrase the question. And so we know that velocity is a distance over a time, right? Since we're solving for time, we're going to need to take that distance and divide it by the velocity. So the distance is 0.3 meters, right? 30 centimeters. The velocity is 200 meters per second. And we're going to get a time of about 15 milliseconds, 0.0015 seconds. That's how long it takes. Doesn't take long at all, right? For that spider to feel the insects, you know, it needs to run over there and grab it quick before it leaves. So about 15 milliseconds. All right. So the key idea here is that the velocity of waves, of mechanical waves, depends on the medium, right? Doesn't depend on what insect, how heavy the insect was, if it flew really hard into the web or not, right? Or if it fell, just, you know, it doesn't matter. None of that matters. The only thing that matters is the tension in the string and the mass per unit length of that string. So to solve the previous example, we treated the wave speed on the string as a property of the medium. This also applies to sound waves because sound is also a mechanical wave. And so the way that we determine the velocity of sound is by examining the properties of the medium. For example, the temperature of the medium, which would be a gas or air, and also the molecular or molar mass of the medium. This has a very similar form that the tension, you know, that the velocity of the wave on the string has. And it's simply the square root of a bunch of parameters that describe that medium. So for a gas, you may recognize some of these parameters from the ideal gas law, right? You might remember that the ideal gas law can be expressed in terms of two different units. One of those units would be using the Boltzmann constant Kb and the molecular mass, little m. Then the other set of units would be using the gas constant R and the molar mass, capital M. Gamma here is present in both equations. This is simply a constant that depends on the gas. It's, I believe, the ratio of the specific heats. So it's something that you would look up on a table. It would not be something you're expected to know or derive. So finally, the temperature, which appears in both forms, is the temperature in Kelvin. Okay, so temperature must be given in units of Kelvin. Wave speed, like we said, property of the medium. So you can use those parameters for air, okay? Temperature of 20 C, convert that to Kelvin, which I think is like 293 Kelvin. You can get the gamma constant for air, which is mostly nitrogen, and you can plug all those values in and get that 343 meters per second value. What you'll notice from the equation for the velocity of a sound wave from above, let me kind of pull it out here and put it below. Notice the dependencies, all right? Proportional to temperature, right? Speed will increase as the temperature increases. However, speed will also increase as the molecular or molar mass decreases, right? Because that would be inversely proportional. Didn't need to write that arrow twice. What the speed of sound doesn't depend on is the pressure, right? Does not depend on the pressure or the density of the gas. The speed of sound in liquid is faster than in gases and faster in solids than in liquids. So maybe you're reading the statement here at the bottom, second to the bottom, right? That the speed of sound doesn't depend on the density of the gas. And then immediately you read this statement right after. And you might find that a little bit contradictory, right? Because what do we know about gases, liquids, and solids? We know that gases are the least dense, liquids are more dense, and solids are even denser. So, you know, if you are reading this and you are genuinely finding this contradictory, you are not going crazy, okay? There is a piece of information that is not given in the slide here, and that is the dependency of the speed of sound on the stiffness, okay, which is an elastic property, right? So when something is stiff, it doesn't bend, right? And when something is elastic, it bends. So that is another contribution to the speed of sound. We're not going to dive into that, all right? I'm just kind of wanting you to kind of, you know, address anything that might come up as you're studying. So what we haven't said in these slides is that the speed of sound we can also describe very roughly as the elastic property of the medium divided by the density of the medium. So these two work in unison to describe the velocity of sound, right? It's not simply the density that changes the speed of sound. It's also the elastic property of the medium. And that's what's changing when you go from gas to liquid to solid, right? Here you can kind of see that illustrated, right? When you look at this table of wave speeds in media, right? So here you have obviously some gases, right? Then depending on the temperature, you got liquids. And finally, you're getting into solid territory. And what happens is you can see the speed is definitely increasing, right? As you go from gas to a liquid to a solid, which, generally when you look at that, you think it's going from low density to high density. And so there definitely is a density dependence, but it's not strictly a density dependence. It also has to do with the elastic or stiffness property of the material. Okay, not something I'm going to be testing on, but just to satisfy your curiosity. So let's do this example. All right, we're on Mars. It's cold, almost as cold as it is right now in Florida. -100 Celsius. All right. The question is, what's the speed of sound? And what's the approximate temperature that it would need to be to double this speed of the speed? So it's a two-part. So we're going to first of all calculate the speed of sound in Mars. And since we're dealing with an atmosphere of entirely carbon dioxide, we're going to use values related to pure carbon dioxide gas. So the speed of sound is, depending on the units you want to use, I'll go ahead and use the gas constant and the molar mass. Take this, copy, duplicate that, bring it down here so we have it. Okay. I'm going to use this definition. So the gamma constant for CO2, it's given to us. It's not something that you are expected to know. And it is 1.3 for carbon dioxide. And the gas constant is 8.314. I'm dropping units just for convenience. It's real easy to go between Celsius and Kelvin. You just take 273.15 and subtract 100 from it. And that's going to give you a Kelvin temperature of 173.15. Finally, we need the capital M value, right, which is the molar mass. And that is something else that you could, if you're real good at chemistry, you could probably calculate it real quick if you remember the molar mass of carbon and oxygen. Or if you don't remember it, you can easily look it up. That's not something that I'm teaching here, right? These are all values that you can look up. So the molar mass is 44.009 grams per mole. That's given in grams, which, in chemistry, they love grams. In physics, we love kilograms. So we need to convert that to kilograms by moving over 3 decimal places. Okay. And there we're able to calculate our velocity. About 206 meters per second. So the follow-up question is, what approximate temperature would the speed double this value? And this is a great question because this is the kind of phrasing that you should expect to see 1 or 2 questions on an exam. And these are, I'm going to kind of show you a strategy that you can use to answer these types of questions. So we start off with the original relationship, and that is the relationship between speed and temperature, right? So here's the original relationship, and I'll use these units. So what you can see is that the velocity is proportional to the square root of the temperature. What we want to know is, what does the temperature need to be in order to double our velocity? So our doubled velocity, I'm going to call V prime. And that is simply 2 times V. So in order to achieve that, I'm going to find the relationship between V prime and V. And so what I'll do is I'll divide the 2. And what I need is V prime over V to equal 2. So now I can substitute what V prime is and what V is. V prime is going to be gamma RT prime over M, right? Because what's changing is my temperature value. So T prime is the variable that's going to represent the change in temperature. And then I'm going to divide that obviously by V. A lot of things are going to cancel, right? Gamma, R, and the molecular mass, or the molar mass, are going to cancel. And what's left is the square root of T prime over the square root of T. And so 2 is simply going to equal square root of T prime over square root of T. So what I need to do is now resolve this relationship and express T prime in terms of, right, my new temperature in terms of my old temperature. So I will move I'll move T, square root of T over here. And then I'm going to square both sides to unlock the square root. And what I get is 4T equals T prime. In other words, my new temperature that corresponds to my new velocity, which is twice the old, is 4 times the old temperature. So this is a standard way. You can think of it as like a ratio, right? You're using the ratio to find that relationship because you'll get a bunch of stuff canceling out and you won't have to worry about, trial and error and plugging in some random T value to see if you get 2V. So, we talked about mechanical waves, waves in water, waves in a string, waves in air, right? Sound waves. Let's kind of talk a little bit about electromagnetic waves. Electromagnetic wave is still a wave. The only difference is that it doesn't need a medium to propagate, right? To move. So for electromagnetic waves, they can travel up to the speed of light. So the fastest that electromagnetic waves can travel is the very same as the speed of light, which is 3 times 10 to the 8 meters per second. So that is the speed of light, and it doesn't matter if it's red light, blue light, microwaves, X-rays. The fastest any of those waves can travel in vacuum is the speed of light, 3 times 10 to the 8. When light is traveling in something other than vacuum, it's going to move a little bit slower, but it's still going to be a very, very fast speed compared to any speeds you see here in the speed of sound. Okay? We're going to talk a lot more about light in the next chapter. This is just kind of a little preview of what's to come. In this example, how far away was the lightning? Okay, so I'm sure you know this trick. When you see the flash of lightning, you start to count, and depending on how many seconds that you count, that is going to tell you how far away the lightning was. Okay, so how does that work? Well, it works based on the speed of sound, right? Because when you see a flash, it takes time to hear the noise, right? Because the speed of light is very, very fast, right? So you pretty much see the lightning at the very same moment that it's striking somewhere, because that light is traveling at 3 times 10 to the 8 meters per second. But you don't hear it right away because the sound is traveling at 343, right? So light is roughly 3 times 10 to the 8 meters per second. Sound, depending on the day, 343 meters per second, right? That is several orders of magnitude different. And so if we want to know how far away the lightning strike is, well, we just need to use the speed of sound, right? Because we know that velocity is the distance traveled over the time it took. We're solving for the distance now. Okay, so we're going to need the speed of sound times, and I'm dropping just units for convenience here, times the time. Took 8 seconds for us to hear that. And so the distance that the lightning strike was away from you is about 2,744 meters, 2.7 kilometers away. Okay? So, we're kind of bringing back a little bit of physics 1 when it comes to relationships, velocity, position, time, right? That's all from physics 1, nothing too crazy. This is just the strategy of solving that problem, okay? And so this is kind of the science kind of behind it, right? So basically 1 kilometer every 3 seconds, or in terms of miles, it's about 1 mile for every 5 seconds. So you take the number of seconds, divide by 5, and that's how many miles away the lightning is from where you are. Okay? So we've spent a lot of time, conceptually going over waves phenomenon, okay? And understanding how wave speed is determined. Now we're going to talk about how to describe waves graphically and mathematically. So we can use snapshot and history graphs to understand a wave's displacement and motion. So this is really a kind of like a conceptual tool. It's not like a real tool that we use to talk about waves, but we're going to go over it briefly. So a snapshot graph, okay, so there's 2 types of graphs. A snapshot graph is a graph of displacement of the wave versus position on the wave, on the object, right? So if we have a string, okay, let me draw the string like this, right? We have a string. Okay, here's the y-axis and this is the x-axis, right? What a snapshot graph is telling us is, right, it's like a picture. A picture is a moment in time, right? At one specific time, this is what the shape of the wave looks like. That's a snapshot graph. So when we have multiple snapshots, right, taking a picture of the wave at time 1, time 2, and time 3, we're watching kind of piece by piece how that wave is moving, okay? And so to relate snapshot graphs together, we need to use the velocity of the wave, right? and we see that the wave has moved a certain amount, right? The peak is here at this location. Now the peak at time 2 is at this location, a difference of delta x. We relate that to the velocity, and then you can find either the time or the position or whatever it is you're trying to solve for. But understanding how these snapshot graphs are connected is really important. They're connected by the velocity of the wave, okay? So we want to consider, when we're looking at snapshot graphs, the motion of the medium, right? We're watching that string move up and down at different times. So what you can do is you can turn a bunch of snapshot graphs into a history graph, okay? A history graph is down here. It's position, or, it's not position, it's motion of one point, okay? The y amplitude of a certain position on the string as a function of time. So the history graph is we're watching one little piece of the rope move up and down as a function of time. And so you can use the snapshot graph to build the history graph, because we know at this snapshot that the height of x1 is, 2, okay? 2. And then at this snapshot, the height of location x1 is 4, okay? And then at this snapshot, the height of x1 has gone back down to, let's say, 2. And then finally, at this snapshot, the height of x1 is 0, okay? And so we use it to build the history graph. So history is a time-dependent graph. Snapshot graphs are a position-dependent graph. Okay? So that's how they're related together. That's what this slide repeats. So in this quick check problem, right, we have a graph. What kind of graph do we have? And so the question is, what graph below represents the wave pulse at t equals -1 seconds? So let's recall the relationship between velocity and displacement and time, right? So what we're going to do is we're going to use the velocity to figure out what the wave looked like how many seconds ago? 2 seconds ago, right? Because delta t is 2 seconds, right? -1 minus a -1, right? Which is 2 seconds, right? That's 2 seconds ago. So our delta t is 2. We're going to solve for delta x, and that's going to be our wave speed, 1 meters per second, times our time, right? Which is 2 seconds. So we're going to look for this wave scooted back by 2 meters, okay? So which graph shows the wave scooted back by 2 meters? So let's take a look at this piece right here, this little jagged piece. So this whole jagged piece centered at 1 is going to be shifted back by 2 meters. So now that piece is going to be centered at -1, right? Which graph looks like that? Graph A. So let's take a look at how we're going to describe waves mathematically. So we're going to assume that the waves are sinusoidal, meaning that they're created by something that is oscillating with simple harmonic motion, and the snapshot and the history graph of these waves are going to be nice and curved like a sine or a cosine function, okay? So this is how we're going to model waves phenomenon as sinusoidal functions. Like I said, this is just a conceptual, right? These kind of snapshot and history graphs that are real jaggedy and discontinuous, these are kind of just conceptual tools, but now we're actually going to model real waves, and many, many waves are easily modeled by sinusoidal functions. It'll match to experiment, okay? So let's break this apart. So this is a snapshot graph, right? because it's y as a function of x, right? It's displacement of the particle from its equilibrium position as a function of position along the string. And so each little part of the string is going to deviate from its equilibrium position at 0 by an amplitude A. So the max height it will reach is positive A, and the min height it will reach is negative A. This max height is called the crest, and the min height is called the trough. We can define this wave by its wavelength. And the wavelength is the distance between successive crests, okay? You can calculate the wavelength by finding the distance between successive crests. And of course, you need to be looking at a snapshot graph to do that, because remember, a history graph has time here, right? And then the distance between crests is going to have a different meaning. We're going to get to that. But right now we're looking at snapshot graphs. And so the distance between crests is going to have units of meters, right, of distance. And so a wavelength is a unit of distance. So we can describe this wave as a cosine function because it starts off at its max amplitude like a cosine does, right? Because cosine of 0 is 1. So A times cosine of 0 will be A, right? Which is certainly that location right there on the graph. So the function cosine, what's inside of it, is going to be 2 pi times x position divided by the wavelength. And what that's going to do is it's going to create this oscillation, right? Because you know that, let's say, a quarter of a wavelength through, right? If this is one whole wavelength here, a quarter of the way through is going to be cosine of pi over 4, right? Cosine of pi over 4 is 0. I'm sorry, pi over 2. Pi over 2, right? Because this entire thing is 2 pi. So for a quarter of the way, we're actually half a pi. So cosine of pi over 2 we know is 0, right? So this stuff here, right, is translating our position into radians, right? So that is how we describe the equation of a snapshot graph, right? What is in our argument is a function of position. Let's look at the history graph. Remember, history graphs have time on the x, quote unquote, axis. So a history graph, we are looking at one position on the string, okay? And we're watching it move up and down, okay? That is one position. And so the history graph, if we were to measure the peak to peak distance on the history graph, that is the period of the oscillation, the time it takes for the little piece of the string to return back to its original position, okay? So that's going to be the time between successive crests. That's going to be the period. And so in the history graph, you have to keep in mind that we are just watching one little piece of string oscillate up and down as a function of time, okay? We can write a function to describe this cosine, right? It's a cosine function, but now in the argument, we're going to have time over the period, okay? You might remember that the frequency is 1 over the period and vice versa, right? And so we can easily rewrite this as a cosine 2 pi ft, okay? In case we were given the frequency instead of the period. It is common to combine the mathematical expressions for the displacement of a part of the string as a function of position and time, okay? So the displacement of a traveling wave moving to the right will have this combined function. And what I want you to notice is this minus sign here. So waves that are traveling to the right will have the minus sign in between the x and the t, and waves traveling to the left will have a plus sign. So it's kind of a little bit counterintuitive, because you might think that, you know, because the velocity is pointing in the positive x direction, there should be a plus sign there, but there's not. There is a really good video that does illustrate that.
Now the negative one goes up again to its starting position over a 2 pi interval. So this is one cycle on the right, one cycle on the left. The function I'm plotting is the cosine function, but I've replaced the variable with x minus something. Now what I've got here is subtracting 0 times pi. So really it's just subtracting 0 initially, and so that's why it looks like an unchanged cosine function, because this just goes to 0. Now let me just show you graphically what happens. As I change the number inside of the cosine, the blue curve is plotting the result. And as I continue increasing this number, you can sort of see the wave sliding to the right. And if you put your thinking cap on and really just like visualize it, if I drag my mouse with a constant sort of speed, then you can imagine this as being a propagating wave going to the right. And that's exactly.
So as you can see, a wave propagating to the right has a phase shift being subtracted from the argument, okay? And so the opposite is true. A wave traveling to the left will have a positive sign. And that's what you see right here. For a wave traveling to the left, the equation gonna have plus sign in the argument, okay? So, right, it's kind of opposite to what you might think, right? Counterintuitive. So let's take a look at this quick check problem. Can we calculate the period of this wave? So what we're given is we're given a y, or a displacement, as a function of position. And we're told that the velocity of the wave is 1 meter per second. So this is a snapshot graph, right? Now, you can't look at this graph and pull out the period directly, because we weren't given the history graph, right? The history graph has time in seconds on the x-axis, and from that, we could get the crest-to-crest distance and get the period. But we don't have that graph. We have instead the snapshot graph, so we're gonna have to be a little creative. We're gonna have to recall the relationship between velocity, position, and time, right? And so the period is going to be the time it takes for the wave to go from one crest to another. So we're going to solve for that time, right? And so let's look at the distance. So the distance it travels from one crest to another is 0 to 2 is 2 meters. The velocity is 1 meters per second. And so our period is going to be 2 seconds. Okay? So not as straightforward, but still knowing the relationships between snapshot and history graph, understanding velocity is position over time from physics 1 is going to help you here. All right? This one's pretty easy. What's the amplitude of the wave? That's always going to be the max, right? It's going to be 1 meter. That's an easy one. What is the wavelength? Well, now we're given a snapshot graph, and you can pull the wavelength directly from a snapshot graph, because the crest to crest distance is going to be the wavelength, which is going to be 2 meters. Okay. So let's do a word problem. we have a boat and there's a sketch here. All right, and so this is a very good sketch on how to solve, to help solve this problem. So we have a boat and it's moving to the right at 5 meters per second with respect to the water. An ocean wave is moving to the left, opposite to the motion of the boat. The waves have 2 meters between the top of the crests and the bottom of the troughs. Okay, what does that mean? That's going to be related to the amplitude, right? Related to the amplitude. How is it related? It's 2 meters between the top of the crest and the bottom of the trough. So that means this entire distance is 2 meters, which means the amplitude is 1 meter, right? The period is 8.3 seconds, so we were told the period. From that, we can calculate the frequency if we needed to. The wavelength is 110 meters. Okay, so lambda is 110. So here's all of our knowns. At one instant, the boat sits on a crest of the wave, and then 20 seconds later, what's the vertical displacement of the boat? So we need to figure out what is y, right, at time t equals 20 seconds. So I've put our problem here so we have a little more room to write. And so what we're going to do here is we're going to use the mathematical description of the wave, okay? And we're going to calculate the height of the boat. So let's write the mathematical description of this particular wave. So we saw in the previous slides that the y position as a function of x position and time, right? This is the combined equation, is going to be equal to the amplitude times cosine function. And what goes inside the cosine function? Well, we have 2 pi x over lambda, and we have a wave moving to the left. So if the wave is moving to the left, we're going to use a positive sign, right, in between the two arguments. And then we have our 2 pi. We can use ft or, right, you can use ft if you wish, or you can use time over period, okay? So we're going to use this to find y, right? Because what we're doing is we're solving for y at some x position at t equals 20 seconds. So we're almost there because we know a, right? A is the amplitude, which is 1 meter. We know cosine. We know 2 pi. Oh, but we don't know x, do we? So we're going to have to do something to figure out x. We know the wavelength. It's 110. And then we have 2 pi t over the period, which was 8.3 seconds. So what we're solving for is we're solving for y, but we have an extra unknown, which is x. So what is x? X is the position of the boat on the wave, okay? Wherever that boat is on the wave, that's how high the boat's gonna be, right? So we're told that the boat is moving to the right with a velocity of 5 meters per second. So v boat, right, is 5 meters per second. And what is that? That is the x displacement of the boat over the time. So what we need is we need to know what is the x displacement of the boat from 0, right? It's delta x because it's starting off here at x equals 0. And as it's moving to the right, 5 meters per second, where is it going to be 20 seconds later? Okay? Where is it going to be 20 seconds later? Well, we can solve for time. We're going to have delta x over velocity. I'm sorry, we're not solving for time. We're solving for x, right? Which is going to be a velocity times delta t. And so our X position is going to be 5 meters per second times 20 seconds. And so our X position of the boat is going to be at 100 meters, right? 5 times 20. So now we know what to put for X. And now we can solve for this Y, because we have our complete function. Okay, I dropped the units here just because it gets real messy. So go ahead and plug that into your calculator. Make sure that you are in radian mode, okay? Anytime you're doing math inside of a cosine, you need to make sure you're in radians. So we plug that in our calculator, and what you get is negative. You can pause, go ahead and pause the video so you can do it yourself. What we get is negative 0.42 meters. Let's go back up here to our picture and see if we can see this in our picture. Negative 0.42. So, right, the boat is moving to the right at 5 meters per second. And so the boat at 20 seconds later is going to be, somewhere at x equals 100. Let's say that happens to be right here. Okay, so the boat is going to be somewhere right here. Well, this wave, though, has moved as well, right? In that 20 seconds, the wave has also moved to the left. So we need to now draw that wave 20 seconds later as it's moved to the left. And it's going to look something like this. So how do I know it looks something like this? Because I know I saw my answer, right? This X position should be somewhere in the negative regime, right, of my traveling wave. And because the wave is moving to the left, I've drawn my peak somewhere to the left, right? And it has moved in such a way that now that X location at X equals 100 is on the negative side of the wave. Does that make sense? The boat is moving to the right. Its X position has moved, but guess what? In that 20 seconds, the wave has also moved and it's moved to the left. So this picture that we're looking at here is not the boat just moving along a stationary wave, right? The wave has moved to the left while the boat has moved to the right. And that is the purpose of using the combined form. Let's do some review, right? The fundamental relationship for sinusoidal waves, we've been doing this a lot, right? Velocity is distance over time. In terms of wave terminology, right, the distance is the wavelength and the time is the period. So this is a fundamental relationship between the parameters that describe the wave, okay? You can also rewrite it in terms of frequency. So the velocity of the wave is simply the wavelength of the wave times the frequency. And this is true for all sinusoidal waves, electromagnetic waves, mechanical waves, sound waves, okay? This is true for any kind of wave. In this quick check problem, we're asked to find the frequency of the wave. And you can look, and we were given another snapshot, right? So remember with the snapshot, it's not a time-dependent function. We're going to have to do a little bit of extra math to figure out what the time-dependent parameters are. So we can get the wavelength of the wave, which is 2 meters, okay? We know the velocity of the wave is 200 meters per second, and we know that V equals lambda over period. So we solve for period. And we get 2 meters over 200 meters per second. And the period of this wave is 0.01 seconds, which would make the frequency 1 over 0.01, which is 100 hertz. Okay, right? Because frequency is inverse, period. So this is a great summary slide, all right? Velocity of waves are determined by the medium. We examined 4 different types of waves, right? Waves on a string, waves, sound waves, okay? Electromagnetic waves. And we also looked briefly, we talked about matter waves, but that we're gonna save for later on, okay? So these are mechanical waves. This is an electromagnetic wave. But you can see that their speed depends on the medium, okay? Fundamental wave relationship in terms of wavelength, period, or frequency, and wave speed, all right? Snapshot graphs, function of x, history graphs, function of t. You can extract the wavelength from the position graph, period from the time graph. So this example is going to be a lot like the one that we just did with the boat. I want you to do this one at home. Or else this lecture is going to be 2 hours long. Okay, but this is a great one to do for practice. Okay, same with this. Do these for practice. Let's talk a little bit more about sound waves and light waves. Right, so sound waves are longitudinal mechanical waves, and that's because what's happening is we are displacing particles slightly to the left and to the right of their equilibrium position, creating regions of high density and low density, right? High density particles, low density particles. High density called compression, low density called rarefaction. And you can express the density in terms of pressure, right? So remember, pressure, is a force over an area, and the denser the particles, the more force is hitting a certain area, right? So if the force is high, the pressure is high, and if the density is high, then the force is high. Okay, so what we're going to be mapping here, instead of a position or a displacement, we're going to be mapping the pressure as a function of position, okay? So here in the compression region, there's going to be high pressure, right? Lots of force, high density particles pushing around, creating force. And then you're going to have a region of rarefaction, which is a low density region where you're going to have low pressure, okay? And then you're going to go high pressure, low pressure, high pressure, and so on. So this is sound waves, right? Pressure oscillates sinusoidally, so sound waves can be represented by a sinusoidal function. Now, pressure waves, that's what we hear in our ear, okay? And we can only, we only evolved to hear a particular set of frequencies. So we can only hear from 20 hertz to 20,000 hertz. And we did a demo in class where we kind of demonstrated that. So in this example, we're going to examine that threshold, apply it to the particular situation of human hearing, and use our fundamental properties of waves to figure out the answer. So the question is, what are the wavelengths of sound waves at the limits of human hearing and at the mid-range of frequency of about 500 hertz? Okay, so well, we are curious about the limits. The limits were 20 hertz and 20,000 hertz. And then we're curious about 500 hertz. And what is lambda? Well, these are all sound waves, right? So they all travel at one speed, which is 343 meters per second in room temperature. So if we want to find the wavelength, then we need to use the fundamental relationship. Okay. Solve for lambda, and we're going to solve for lambda for each of these frequencies. So F1 is simply going to be 343 over 20. And I'm just dropping the units just for speed and convenience of writing. Okay, right? There we go. There's our frequencies. I'm sorry, wavelengths. Wavelengths, right? That's what we're solving for. There we go. So those are our wavelengths, right? Meters per second divided by inverse seconds is going to leave us with meters, right? So we plug those into the calculator and we're going to get our wavelengths. And the result is 17 meters for a frequency of 20 hertz, 0.7 meters for a frequency of 500 hertz, and 0.017 meters for a frequency of 20,000 hertz. So you can see that increasing frequency gives us a decreasing wavelength, and that makes sense. Because if this is constant, right, if the frequency is going up, then in order to maintain a constant velocity, lambda must go down, right? Because V is constant, 343 meters per second. So you might have heard of ultrasound, especially if you're considering pursuing the medical field or if you've been to the doctor for any, hopefully not too terrible of a reason. You might have experienced ultrasound. So ultrasound are high frequency sounds above our range of hearing, okay? And dolphins use ultrasound to see in water, right? I mean, you've opened your eyes underwater before. Maybe not, okay, but maybe you have. Things look blurry. Things look messed up, right? In order to be able to hunt efficiently, dolphins and other, animals in the ocean have developed echolocation, and they use ultrasound frequencies. They send it out, bounces off an object, and it comes right back, and they inherently understand the velocity of that wave, and so therefore they can figure out how far away the creature is by how long it took to get that signal back to them, kind of like the spider, right? The spider with the insect. So anyway, ultrasound is simply a device that creates frequencies higher than about 20,000 hertz. And that device, you rub on your belly, and if you've been pregnant before, you get that device, it rubs on your belly. It's sending out frequencies somewhere in the range of 20 to 40,000 hertz. And that wave is going to strike something and bounce back into the receiver. And based on the time it took to get that sound wave to go back, we know how deep that object is in the body, okay? So ultrasound frequencies behave just like sound, right? They move at a particular velocity depending on the medium. So if the medium is human skin, human water, right? The juice, right? Whatever, the liquid of our body, right? We kind of know what the velocity is in that kind of medium. And so we're able to determine, how far away things are, depending on the time it takes for that to come back. So let's take a look at this example. So to make a sufficiently detailed ultrasound image of a fetus, a physician has decided that a wavelength of 0.5 millimeters is needed. What frequency is required? Okay, so we know that the fundamental relationship between wavelength, frequency, and speed is this. But what we don't know, what we need to look up is, well, what is the speed of sound in human tissue? Okay, so we don't know that. It's not the same of the speed of sound in air, right? Because air is a lot less dense than human tissue, and human tissue is mostly water. So it's probably going to be something close to water. Let's take a look at that table a few slides back. Okay. 1,540 meters per second, right? Very close to water, right? Human tissue, mostly water. All right, so our velocity for ultrasound is 1540 meters per second. The physician determined a wavelength of 0.5 millimeters, which is 0.5 times 10 to the minus 3 meters. The question is, what's the frequency? We can quite easily solve for that, right? 1540 divided by that little number. So we're going to have a pretty high frequency, right? Which is what we expect. Remember, we want some number greater than 20,000. The frequency is 3.08 times 10 to the 6 hertz. Okay? So that's about 3 megahertz. Mega is 10 to the 6th. All right. So, and 20,000 is 2 times 10 to the 5. So about 100 times faster than, 100 times higher frequency than what we can hear. That's why we don't hear anything when we do ultrasound. You don't hear any high-pitched whining or anything like that because our ears are not equipped to interpret sounds with that higher frequency. Let's talk about electromagnetic waves, right? So frequencies even higher than that start to enter into the electromagnetic spectrum, okay? So super high frequencies are going to be electromagnetic waves. And electromagnetic waves, like we mentioned before, include visible light, radio waves, X-rays, microwaves, UV light, okay? And all electromagnetic waves, if they're going through vacuum, are going to travel at the speed of light, c, which is 3 times 10 to the 8 meters per second. So electromagnetic waves have extremely short wavelengths, right? They have short wavelengths, which means they have high frequencies, right, in order to maintain constant V. So they're going to have much higher frequencies than ultrasound, which was in the megahertz range. This is the electromagnetic spectrum. Okay, so we were in the megahertz range. So we were somewhere over here for ultrasound, right? Anything higher than ultrasound is going to be in the electromagnetic spectrum. So we start off with radio waves, okay, with a frequency of 10 to the 8. And then the corresponding wavelength would be about 3 meters. Microwaves, so the waves that your microwave uses, a frequency of roughly 10 to the 10, which is a little bit smaller of a wavelength. And then finally we get into infrared, visible light, ultraviolet, and X-rays, and then there's even more down this way. But those kind of frequencies are more closely related to phenomenon in outer space. Not too much the subject of our course. All right, so higher the frequency, you're getting an electromagnetic spectrum, and the wavelengths are going to get smaller and smaller because of the inverse relationship between frequency and wavelength. Okay, either way, right? As long as it's inverse relationship. So this is a very straightforward example. I'm going to skip this one for now. This lecture is running quite long. So obviously we're going to be able to apply the same fundamental relationship. Doesn't matter what kind of wave it is. Same for this one. Okay. The last thing I want to get into, and we will cut this after this lecture after this section. So we're going to include 15.5, is the relationship between energy and intensity of waves. All right. So a traveling wave, as we saw before, transfers energy from one point to another. We're going to classify the power of a wave as the rate at which the wave transfers energy. So this is a little bit of a recall. Power is energy transmitted over time, okay? So power is energy over time. And unit analysis is going to be really important for this section. It's going to help you out. So power is energy over time, all right? And we're going to characterize how the power of the waves gets transferred or spread out by waves. So we need to talk about different kinds of waves, all right? Circular waves. So circular waves, I hope it's not too confusing. What we're looking at in this picture is a source of a disturbance, right? Let's say that I throw a rock into a pond, and those waves are going to emanate from that source in a circular fashion, right? A two-dimensional circular fashion. And so what are we looking at here? These blue lines are going to be the peaks of the sine wave, right? You can see how the peaks line up, the peaks of the sine wave, and there's a whole bunch of them, right? Whole infinite number of sine waves emanating from the source. We just need to look at one. And so a circular wave just means that you have an infinite number of sine waves that are emanating from a source, you know, in all 2D directions. And so creating successive circles. These are called circular wavefronts. Plane waves, all right? Pretty much all wavefronts can be approximated as plane waves if you are far away from the source, right? So if you are very far, so let's say that, you know, you are, here's like the water, and then you're standing here on the beach, and you throw a rock really far away. And what you see are these circular, right? They're circular, but what you see, because it's so far away, are just waves coming at you, right? Flat waves, like when you're at the beach, and the waves that you see coming at you don't look circular at all. But they are caused by something deeper in the ocean, and by the time they reach to you, they look flat. The curvature has disappeared. So we can just approximate waves as planar waves, meaning the wavefronts are all parallel to each other, right? So these are all the crests or the peaks. And remember, each crest or peak is a wavelength apart. Spherical waves are simply three-dimensional waves, right? Pretty much waves in, you know, in air or in space, like light waves and sound waves. Those are going to be three-dimensional waves because they're able to move in all three dimensions from the source of the disturbance. So, right, we're going to be treating these waves as plane waves, and we're going to be just basically under the consideration of us being far away from the source. So now that we kind of set that scene up, let's define the intensity, all right? The intensity of a wave is going to be how much power is being spread out over a certain area. And so we have those three different geometries to consider, okay? The planar, the circular, and the spherical geometry. So the intensity for a planar geometry is going to be the power over the area, which is simply going to be the area of a rectangle, right? The area of a plane, right? Planes are basically rectangles. So the intensity, this is where the units come in. The intensity is power over area. And then what is power? Power is energy over time. So energy over time times area is an intensity. The units of I, of intensity, are watts per meter squared. So a wave that is focused on a small area, right? A small area is going to have a high intensity, right? Because if the denominator is little, the left-hand side of the equation is going to be big. And that's the opposite is true, right? If some power is spread over a large area, well then a very small intensity is hitting that area. In this quick example, just to put that, you know, kind of like develop the language, the new language that we're learning, let's say that we have a laser and it's emitting 1 milliwatt of power. right? That is spread out over 1 millimeter diameter. What is the intensity of the laser, right? Intensity is power over area. The power is 1 milliwatt, which is 1 times 10 to the negative 3 watts. The area is the area of what? So we were told diameter, right? So our area is a 1 millimeter diameter circle. The area of a circle is pi r squared, pi d squared over 2, right? So that's going to be 3.14 times 1 millimeter. And that is going to be the area. Which is 7.85 times 10 to the minus 7 meters squared. And so then we can calculate the intensity. That's going to give you an intensity of 1,270 watts per meters squared. So, right, in this case, our area was a circle. So, the kind of difficult, part of this problem is making sure you're using the correct area. Otherwise, it's a very straightforward calculation. So let's talk about spherical waves. So if the source is a spherical wave, right, meaning that the source is either a sound wave in air or a light wave in air, right? It's able to move in all 3 dimensions. It's not restricted by a string or a sheet of water, right? When you have a string, you're restricting the wave to exist only in 1 dimension. When you have a surface of water, you're restricting the wave to exist only in 2 dimensions, right, on the surface of the water. When you have sound waves or electromagnetic waves, they're able to move freely through the medium in all 3 dimensions. So that's going to be a spherical wave. And so the intensity is going to be calculated by the power of the source divided by what? The surface area of a sphere, which is 4 pi r squared. So the intensity can be calculated, right, in that way. So if a source is emitting power, okay, a constant power, like you have a laser that is, it's engineered to create 1 milliwatt of power, right? And that power is being spread out over that 3-dimensional area. We can develop a relationship between the intensities at different distances, okay? And that is given by this relationship right here. And so where does this relationship come from, right? So if the power is constant, then the intensity at R1 is going to be that power divided by 4 pi R1 squared. Then the intensity at R2, right, if the power is constant, it's going to be P over 4 pi R2 squared. If we divide those two, to get I1 over I2, you're going to see all sorts of things cancel, right? And you get this relationship right here, right? I1 over I2 is equal to R2 squared over R1 squared. So that's where this relationship comes from, right? It's simply an application of intensities under a constant power, a source of constant power. So apply that to these example problems, okay? Don't have a whole huge amount of time to go over them, but do this example and apply the ratio. The last thing I want to talk about very quickly, not going to be tested on, okay, but appears on the homework. So I'm going to quickly go over how we describe the intensity or the loudness of sound. So we use a different scale to determine the loudness of sound. Generally, increasing sound intensity by a factor of 10 results in a perceived loudness by a factor of 2. So the scale is kind of off, right? The physical scale and the biological scale are off. And so we use this sound intensity level to measure the loudness of sound, okay? It's on a log scale. So do you know why we use log scales sometimes? Log scales, this is in general for anything, log scales make little things big and they make big things little. And so we're using this logarithmic scale to make the subtle differences between loudness big, right? So that we can kind of see the differentiation better, okay? This is called the decibel scale, which you might have heard of. So the threshold of hearing is the lowest intensity of sound that can be heard, okay? This is kind of like our 0. This is like a 0 on the loudness scale. And so for the average human, the threshold of hearing, which we denote by I naught, is 1 times 10 to the minus 12 watts per meter squared, right? That's the intensity units. We express the sound intensity level as the following, beta. So the sound intensity level in decibels is beta. Beta is equal to 10 dBs times log base 10 of whatever the intensity of the sound is divided by the threshold. That's the sound intensity level in units of decibels. So we just have to do a little bit of mathematical log base 10, multiply it by 10, right? So this is a quick reminder of how logs work, right? Some basic logarithmic algebra. So if you express a number as a power of 10, then the logarithm is the exponent. So log base 10 of 1,000 is just like saying log base 10 of 10 to the 3, right? Because 10 to the 3 is 1,000. And what the log base 10 does is it pulls out whatever the exponent is. All right? And so what we're doing is when we're dividing I over I naught, we're pulling out the exponent and multiplying it by 10 decibels. Okay? So at the threshold of hearing, where I equals I naught, what is the sound intensity level? Well, remember it's 0. So let's make sure the math jives, right? I naught over I naught is the number 1. The number 1 is equal to 10 to the 0, right? Log of 10 to the 0 is pulling out the exponent, and the exponent is 0. So the threshold of hearing corresponds to a sound level of 0, which is 0 decibels. So the decibel scale, as it appears right here, okay, can be rearranged to solve for the intensity. So you can do that by recalling some more log algebra, log rules, right? 10 raised to a log is simply going to be what's in the argument of the log, x. So you use that and you can solve for the intensity if you know the decibel, right? If you know the decibel. So here's some relationships between the decibel scale and the intensity of sound that is produced. So a whisper is about 20 decibels. 20 decibels is about 1 times 10 to the minus 10 watts per meter squared, right? That's the intensity. Niagara Falls, okay? 90 decibels, all that water falling down, hitting other water, produces quite a loud sound of about 90 decibels, which is a intensity of 1 times 10 to the minus 3 watts per meter squared. When things start, your ears start hurting as a result of a sound, okay? That is 130 decibels, which is about an intensity of 10. So you can see how a log-based scale helps to make big differences little, right? And little differences big, right? Look at the huge range of intensities. We go all the way from 10 to the minus 12 to 10 to the plus 1, right? A decibel scale takes big differences and makes them small. So the decibel scale is going to instead of going over an order of magnitude of 13, we're only going from 0 to 90, right? So that's what a logarithmic scale does to data. I'm sorry, to 90, to 130. So here's a summary of this section, right? Intensity is a power over an area, and the intensity is going to depend on what area is being covered by the wave. So for a plane wave, the area will be a rectangle. For a circular wave, the area will be that of a circle. For a spherical wave, the area will be that of the surface area of a sphere. Okay? The decibel scale is how we compute sound level intensity, okay? And so you can go back and forth between the decibel scale and the intensity using these equations. So do this example, in the long version of the slides, you will find the answers, step-by-step answers. So this is a great example to do before moving on to the homework to make sure that you understand the very basic concepts involved, okay? And then the homework will be 1 or 2 steps more complicated. That's the idea here. All right, so that's all that we're going to cover for chapter 15.